Not gonna be here today.
I wasn't gonna be, and then move
Here.
some stuff around, yep.
Okay, all right. Okay, the one thing that becomes important in chemistry is also gonna be the concentration of something. And that's not just in chemistry, that's in everyday life, correct? So you're kind of concerned about concentrations. Gasoline, milk, all this sort of stuff. Have you ever been to I don't know if it happens much now anymore, but you go to a fast food restaurant where you get your own soda fountain and it isn't quite mixed right? You ever experienced that? It's disgusting, right? It's so the concentration's off. It's either too concentrated or it's not concentrated enough. And that has to deal with solutions, right? So in this class, what we're going to talk about is we're going to talk about homogeneous solutions. We're not going to talk much about heterogeneous solutions, except when we get to Chem 2, when we talk about equilibrium. Now, you did get experience to heterogeneous solutions when we did precipitations, right? Because in that case, you had a liquid phase and you had a solid phase. So that would be a heterogeneous solution because it's a multiple phase. So here we're just going to be talking about homogeneous solution. And this will be a mixture of two or more substances that are going to be in the exact same phase. Now, air, believe it or not, is actually a homogeneous solution because everything is a gas, right? We have mixtures of oxygen, nitrogen, and argon, some CO2, and some water. If any of you happen to have a gold piece of jewelry, that is a solution because you don't buy gold jewelry that's 100% gold. Everybody knows that you can get 10 karat, 14 karat, 22 karat. And what they do is they put metals in, or particularly silver, maybe some platinum, to harden that gold because gold is amazingly soft, incredibly soft. So that would be a solid solution. My wedding ring is not a solution. It's only one element. It's just titanium is all it is. So it's not a solution. My wife's though, that would be a homogeneous solution because it's got gold and some silver, I think some platinum in there as well too. Now a solution is made up of two things. It's gonna be made up of the solute. That's what gets dissolved into then the solvent. So solvent is usually that which is the solute is dissolved into. And for the most part, our solvent is going to be water. We're going to use water as our solvent. Okay. We're going to use water as our solvent. So where we're going to go with this today, and if we get it finished, fine. If we don't, no big deal. We'll finish it on Monday. We're going to do some calculations with some concentrations. I'm going to go over these. We'll do some concentration calculations. We'll do a dilution concentration solutions. So we'll do some dilutions. And then last, I know everybody's just dying to do this. We're going to do solution stoichiometry. Does that sound amazing? Yeah, I know. I get it. I'm sorry. I'm trying to make this as exciting as possible. So what is a concentration? A concentration is going to be how much solute is put into a solvent. All right. So how much solute, the amount of solute that gets put into a certain amount of solvent. All right. Now the one that we're going to, so there's multiple different ways in which you measure concentration, but the one we're going to deal mostly with will be molarity. All right. Now molality, we're only going to deal with this at the beginning of Chem 2, and then we're done with it. In the 20 plus years I've been a chemist, I have only used this, I think, one other time other than when we talk about colligative properties, which we'll talk about in Chem 2. So this doesn't get used a whole lot. In the environmental world, some of you are interested in environmental chemistry, environmental science. You may use molality a little bit there. But the two, and then the one that we most as consumers outside of this that we work with is going to be percentages, all right? So this could be mass percent, volume percent, could be mass per volume. This becomes the one that is actually most prevalent in the consumer world. And then normality, we would talk about that if I was 80 years old. So next year when I turn 80, we'll start talking about that. Actually, I won't. It's a joke. We don't talk much about normality. All right. I remember when the first time I was introduced to this, the guy I swear was pushing 80, and you see it a lot in chemical, when you buy acid, you know, what, they'll show it as a normality, but for the most part, normality is almost the exact same as molarity, except it has to do with a stoichiometric coefficient difference, so. The one we're gonna deal most with will be molarity, all right, we'll deal with molarity, that would be the one we deal most with. All right, and it's given a symbol capital M or the square brackets, all right? So the capital M stands for molarity, the square brackets will stand for molarity. The lowercase m stands for molality, right? The units for this are going to be a mole per liter. The units of this will be a mole per kilogram. And then this is just simply going to be a percentage. And then normality, I'm never going to ask you anything on normality. And I would, yeah, I think other than that one class of all the years of college I went through, all that stuff, I have only, just in that one class have I ever dealt with normality. It's not that used that often. Oh, good grief, yeah, it always the heck of bad. All right. Okay, so what is molarity? Molarity is the moles of solute over the liters of solution, right? So it's gonna be the moles of solute over the liters of solution. All right, that's what it is. So units of molarity is moles per liter. We'll talk about that quite a bit. And we'll do a lot with that. So like I said, molarity is what gets used the most, okay? Molarity is what gets used the most. And I think that I'd venture to say, I haven't done much work with biology, but I would venture to say if you're working with, if you're interested in environmental science, you probably won't use a whole lot of molarity. My guess is you'd probably use a lot of percent concentration. What you'd use. In the healthcare field, you would use a lot of percents. In fact, molarity is kind of exclusive to just chemistry. It's very powerful for chemistry because we think about things mostly in terms of moles. But molarity will be the big thing we talk about. We'll do this a little bit. Molality is a little bit different. It's going to be like once in the moles of solute. However, instead of liters of solution, it's going to be kilograms of solvent. Now, in this case, this is the liters of both the solute and the solvent. So it's going to be both the solute and the solvent for the liters of solution. This is just the kilograms of solvent. Now, there are times in which the molarity and the molality will have the exact same value, but that only occurs if the density is going to be the same. If the density changes, then they won't. And we'll do some calculations next semester, not this semester, but next semester. I believe it'll be next semester, looking at molality and molarity and doing this concentration. But we'll talk about this in the second semester, just at the very beginning, and then we're done. But let's say we want to compare 250 milliliters of a potassium dichromate solution. How much potassium dichromate should be added? So how do we do this? Our hands. We want K2Cr2O7, right? Now what we want is we want to come up with 0.1 molar potassium dichromate solution. So we want to go to grams of potassium dichromate because we want to know how much of the potassium dichromate do we have to add to 250 milliliters of basically solvent. So we start with 0.100. Now that big capital M, that capital M is really a moles potassium dichromate over 1 liter. That makes sense? And what we're going to do is we're going to go molarity to moles and then to grams. That's what we're going to do. This is not stoichiometry at all. We're not doing stoichiometry. Stoichiometry is relating one substance to another substance. That's not what we're doing here. We just want to simply calculate how much potassium dichromate should we add to that volume of and 0.1 more solution potassium dichromate. Now, if I multiply by the volume that's required, it becomes 0.25 liters. Now my liters cancel. Now I'm in moles. Now, if I want to go from moles to grams, I simply need to calculate the molar mass of the potassium dichromate. Does this step make sense? Yes, no? At not quite 8 in the morning? Right. Now we calculate the mass of potassium dichromate, so it'd be 39. One. Plus 2 times. Chromium is 2 plus. 7 times 16 is equal to that. That's 294. So 1 mole. Potassium dichromate is 294.2 grams of K2Cr2O7. So now my moles cancel with my moles in. That makes sense? So now we're in grams of potassium dichromate. So if I want to make this solution, yeah,
How'd you know what it is?
multiplied by the molar mass.
Okay.
So remember, at this point, once we're here, we have moles. And then to go from mole to grams, you gotta use the molar mass. Yeah,
But this is the zero part of the whole.
that's gonna be the 250 milliliters. So I just converted it into liters. Good question. Yeah, good one. I just, since I have a liters here, I gotta have this volume in liters so it cancels out. Yeah. So if I were making this, what I would do is I get a volumetric flask. The volumetric flask has got a kind of a big bulb down here, really narrow neck, and it's got a little, if you look at it very carefully, we'll work with some, for sure next semester, we'll look at, it has a ground ring that will measure exactly what the volume is. So we'll take a 250 milliliter volumetric flask, add just a little bit of water into it. Then we would add the 7.355 grams of potassium dichromate and then fill up to that mark with water is what we would do. And that's how you make that solution.
This might be a dumb question, but how can you get rid of zero in the 250 when you convert it to?
Here?
How can you just get rid of it?
Well, it doesn't change the calculation at all. Right, so if I take 250 milliliters. Convert it into liters, right? 1 liter is equal to 1,000 milliliters, and that gets me 0.250. That zero doesn't do anything for the calculation. So, yeah. Okay, that's fine. Happens to me all the time. It's too early. It's way too early. Does that make sense? We're good? All right. So that's how we make a lot of solutions. It sounds kind of weird, but I actually do enjoy making solutions. I don't know why, but I really do enjoy it. See how active I can get. Now, one thing that we do quite a bit in chemistry, and you do a lot, if any of you are interested in becoming a pharmacist or anything of that sort, you would do a lot of dilutions of a pharmacist. You get a lot of medications and you do have to dilute them. So, just as we were talking about with the fast food restaurant and soda fountain, what they actually do is they actually buy the syrup, the flavoring, the coloring, caffeine, all the stuff that comes in that soda pop, but it comes in as like a syrup. And then the machine actually mixes the syrup with the water, hopefully at the right consistency and the right concentration. And of course, then they would have to add in the carbonation, so it would taste like whatever soda pop you want anywhere in the world. Does that make sense? Right. Except once you travel outside this country, then a lot of times they don't use high fructose corn syrup, which is what we use for sweetening. They actually use real pure cane sugar, so it might taste a little bit sweeter. But that's going to be based on that mixing is going to be dilutions. I used to work through a convenience store, bait shop, and that's what kind of got me through college. Was that money from that? But I don't ever remember, we had a fountain machine, but I don't think we ever had to change it. I think the distributors would come in and change it, but they bring in like I don't know if it's this way anymore or not, they'd be a It's a aluminum stainless, cylinder, diameter by 8 to 10 to 12 inches and be about a couple feet tall. Was that, any of you work at fast food restaurants? Is that what they do? Is that what, when they change those out? I think it's. Like, reminds me of a cake, like you're in Minnesota. Cakes everywhere. I know I'm not supposed to say that word here, but they exist. But it actually looked like a cake, so. I think the two drunkest states in America are probably Wisconsin and Minnesota. Wisconsin by far being the top. But I remember they were aluminum, they were about 10 to 12 inches in diameter, a couple feet tall, something like that. And the distributor would come in and plug in the hoses and then in the insert would mix the carbon dioxide, the water and all that. So now we won't work a whole lot with the percent by mass, but that's gonna be the mass decided or the mass of solution. Now, and as I said, as consumers, you'll mostly work with percent quite a bit, and it won't be just mass, you'll also work with volume, but we'll get that in a little bit. If you're gonna make dilution, just like in that machine, you get something that's really concentrated, and then you add more solvent to it to dilute it. Does that make sense? So that's what you ultimately do. That's what a dilution is. You don't change the number of solute molecules, you change the number or increase the number of solvent molecules. Okay? So you don't change the number of solute molecules, you just add more solvent to it so it becomes more dilute. Because we can't take out the solute molecule. That would be too hard. Okay. So what we do, you just simply add more solvent molecule. So in solution, the number of solute molecules does not change. However, the amount of solvent does, and the amount of solvent is going to increase. I think something that would be a very important equation you always want to keep in the back of your mind for this entire year is M1V1 equals M2V2. This is going to be the equation of dilution. Now, M is going to be your concentration, V is going to be a volume, M2 is going to be a concentration once again, and V would be another volume. This should be V1 and V2. I typically what I do is I treat this as the stock solution, so this being the most concentrated, and this would be after the dilution. What do I say about this? Oh, now M here in this case represents molarity, but you can use any unit of concentration you want. This is not exclusive to just molarity. You could do molality, you could do percent mass, percent volume. Matter of fact, the volume itself doesn't even have to be in a metric system. This equation works great even in the English system, and you don't have to change anything. So the nice thing about this equation is you don't have to do any converting. That's what I like about it. You don't have to do any converting. What molarity is obtained when 37 milliliters of 4.5 molar sodium hydroxide is diluted to 100 milliliters? The molarity obtained, so we have M1 V1 equals M2 V2, all right? M1 is going to be the concentration of the stock solution. So this is going to be the volume of the stock solution. This is going to be the volume of the dilution. Does that make sense? So our M1 is going to be 4.500 molarity. Our V1 is 37.00 milliliters. Our M2 is what we're looking for. So we're trying to find M2. And V2 is going to be 100 milliliters. Does that make sense? All right. We just start plugging in these numbers. So 4.500 molarity. I'm just going to leave this in terms of milliliters. Even though this M is a mole per liter, I can just leave this as milliliters because you'll see once the math occurs, the milliliters will cancel. So I don't have to change that. M2, and then this is going to be 100 milliliters, right? And all I'm gonna do now is divide this whole thing by 100 milliliters. Well, my M2 that I get is 1.667 molar or 5. Good, that makes sense?
Mhm.
Yeah,
I guess you divide it by the 100 milliliters, that's because it says it's diluted to.
yeah. So it says it's diluted to, that's gonna be the volume of the dilution. So when you're done doing the dilution, you're gonna get 100 milliliters total.
Will those two numbers always be the same, like the V2 and the bottom? Like.
Well, this is just the math thing, right? So I wanna get M2 by itself. How do I get M2 by itself? I have to divide by the 100. So it might be a case where you. Most of the time you do dilutions, the majority of the time you do dilution, you actually solve them for V1. I'd say 100% of the time I do these, you're always solving for V1. But in this case, Ray, it's just the math, and you want to get the M2 by itself, so you divide by that volume. In this case, if it's V1, I make lots of solutions for this class, but I love making solutions. It's weird. It's kind of bizarre, but you divide them by the M zone, get that by itself. Yeah.
How do the two correlate? So how does mass one and volume one correlate to mass two, volume two? In the moles to
Because you got the same. So if you were to do this equation, if you were to multiply this, what you get here. This would be the moles. Of solute, right? What would you get here? Moles of solute. So let's just say, for example, if you multiply these two together, right? So if you take 4.5 times 0.037, what you get here, this is equal to on this side 0.1667 of 5. I don't know why I keep writing 7, 5 moles of solute. Over here, you get the exact same. And so if you take this, your concentration M2 multiplied by 0.1, over here you get 0.1665 moles of solute. So how they relate to one another is this is moles of solute and that's moles of solute. And that goes back to the statement here, in dilution, the number of solute molecules does not change. So here we just showed that this is the moles of solute after the dilution. This is the moles of solute before the dilution, and the number doesn't change at all. Yeah,
and that'd be after converting them all to liters.
yeah.
So that
Is
was
this-
enter the point one instead.
Needs to be 0.1, yeah, because this is moles per liter. And so how I did this, this number is I had to multiply, multiply 4.5 by 0.037. You can leave this in milliliters, for example, if you were to take the molarity and you multiply it by milliliters, what you end up getting is you get millimoles. Which makes sense. You can,
Okay.
oh yeah, if you were to take chemistry with me and take analytical chemistry with me, we will mostly talk about millimoles. And it's kind of cool. I mean, it's really neat because you don't have to do any of the conversions. You don't do any conversions. You don't do a conversion at all. You just, we just take this times that. It'd be, what would it be? 160, what would it be, 166.5 millimoles. But you can do that. I mean, there's nothing wrong with that. Milli just means 1,000th is all it is. You're just doing that. But it's actually a very useful unit. Yeah, it's really a nice unit. Just once you start in this stuff long enough, then you just start doing the math in your head. You're literally moving the decimal point left and right. That's it. That's all it is. Good. So far, so good. Good questions. maybe next week, remind me, I'll show you the greatest, the most important video on the units of measure that exists, all right? I keep forgetting to do that, it's amazing. I show it. We'll have to do that. We'll go with this? Does that make sense? All right, I know what you've been saying. Oh my goodness, this is why we come to this class. We want to do stoichiometry, right? That's sarcasm. I don't like stoichiometry either, but I have to do it. I don't like paying taxes, but I have to do that somehow. See, I know I don't have to, but you know, I'm not real pretty, but I'm kind of pretty for prison, so I don't really wanna. I don't understand why I have to pay property tax on a place I own, you know, I guess I don't own it. I do, but I am craziness. Take my kids up to school. I always drive by this house, the guy says, get rid of property tax. Yeah, I said, let me get rid of property tax. I guess there's a movement in the state to do that. Yeah, I know, my folks' place is, what is it? 3-4 times more valuable than ours, because they're on a lake in Minnesota. And Minnesota, like the land of 10,000 taxes, our taxes are more than theirs. And we have a little tiny house, nothing, you know, we're not on a lake, we're just a little, barely 2,500 square feet, like really small. Matter of fact, the four of us were in the kitchen. This is right. Now it's okay. Bumping into each other. Anyway, let's do some stoichiometry. How'd that sound? Yeah. Go team, go. Oh, all right. Okay, anytime you see excess, we should celebrate for joy, because we don't have to do limiting reagent problem. But however, we do have to write a balanced equation, right? So we're just gonna do this one. I'll knock it out in a few minutes. It won't take long, and then we will do the quiz and you can get out of here. How's that sound? Like a plan? All right, so calculate the mass in grams of tin 2 sulfide, which should be formed by the complete reaction of 120 milliliters of 0.5 more tin 2 nitrate with excess H2 or hydrogen sulfide. All right, we're gonna write balanced equation. Then nitrate of the hydrogen sulfide is going to give us tin 2 sulfide. That's going to be a precipitate sulfide plus 2HNO. Yeah. So that's going to be our balanced equation. Okay. So far, so good. Now, what's the cute little song we've seen for stoichiometry? Grams the moles, moles the grams, right? The same thing, right? That was the lullaby I'd sing to my kids when they couldn't sleep. Kind of a goofy story. My daughter's always had a hard time sleeping, so we just took her out of the hospital. And she wasn't even a week old, she could not sleep. And so what I did is I started telling her the first 3 laws of thermodynamics and explaining them to her. My dad just shook his head and said, that's child abuse. She fell asleep in the middle of the second one, which is really the most exciting, but the most bizarre one, right? You know, entropy. He said, oh, that's child abuse. I thought, yeah, you should know, you raised me. I should have said, no, I know what child abuse is, you raised me, but that's kind of fun, right? All right, so our cute little song we're gonna do is we're gonna do molarity to moles to grams, right? That's what we're gonna do. And it has, once again, 4 parentheses, just like we had before. Okay? So we start with what we're given, right? 0.5 molar tin 2 nitrate. This is going to be 0.5 moles tin 2 nitrate over 1 liter, right? If we multiply by the volume, that gets rid of the liters. So 0.12 liters, right? That gets rid of the liters. So now we're at moles, that, I missed, how could I miss this step, Moles per gram. That would not have made a good lullaby, I guess, now. Now we're in moles of tin two nitrate, we have to go to moles of tin two sulfide. So now we just do the balance equation like we did before. So this becomes 1 mole tin two nitrate to 1 mole of tin two sulfide. And now we just have to multiply that by the molar mass of tin. I should know, yeah, how many? 7. It's 32. So if I need 7. What this will produce, it'll produce 9.042 grams of tin two sulfide. All right. If you forgot to calculate, no big deal, just show your work. Does that make sense? The answer is worth very little. Is actually in my mind worth very little once I read, just see the work. Yeah.
So just on when it goes from mole to mole, that, is it always gonna be 1
No, it's what it was stoichiometric coefficient.
Okay, do you have to write the whole thing down?
Yeah. That's, it's always nice. It's always nice to have a balanced equation because those were the ones are. Yeah, good question. All right, so if you don't have a calculator, don't worry about it. It's really not a big deal. I got periodic tables for you. There's your periodic table, exactly. They don't want you to have any notes. And just show your work. That's all I want. The answer, even on exams, is not worth many points for them. We're not engineers. We're not the right number. All the numbers. Oh my goodness. Oh. We got enough exams.
Actually.
Oh, it's just the first one. Yeah.
Then when you're done, you can leave. See. Say what? I know. And you need a few. Yeah. Any problem? No. Yep, and I'll get you a periodic table, so I'm using this thing. Who uses periodic? Good.